You all got very, very quiet. That was awesome. Thank you all for being here. My name is Cinnamon Moffat, and I'm going to be your host for today's seminar. Again, thank you for being here with us. This is a hybrid event, so we have folks online and folks in the room. A couple of quick instructions and reminders because I see some new faces in the room. For folks online, if you have any questions, just go ahead and put those into the chat box. We have a volunteer in the room, Roseanne. Hey, Roseanne. She will make sure that she helps you with any of those technical questions. And then if you have any questions for today's speaker, if you put them in the chat box, Roseanne will read them out when we get to question and answer, so our speaker today can get to those questions. For folks in the room, when we get to the question and answer, if you just raise your hand, I'll bring you this mic, and that way folks online can hear the question and participate with us as well. But again, thank you for being here. I wanted to do a couple of quick announcements, and I'm talking quick because I'm really excited about today's talk. A couple of things that are coming up that I wanted to promote and remind folks of. Next Tuesday is our Science on Tap event. Bob Cowan and Sue Spinagle are going to be talking about their plankton research. So these events, these Science on Taps, happen here in this building and are more of a public-facing event. So anybody is welcome to join. It does have an online presence as well. So if you're curious about being here or joining online, you can go to the HMSC website, go to the events page, and you'll be able to find information about Science on Taps. But this should be a really good one. It'll start at 6 and go to 7. And Bob and Sue are amazing speakers, so I hope you join us for that. The other thing I wanted to put a little plug in is Marine Science Day is just around the corner. If you're not sure about this event, it is our big open house here at Hatfield. And it's a time to celebrate you all and to celebrate our science that we're doing here. So please come and support us. This is on the 12th of April. If you're a researcher and you haven't already put in your request for a table, that way you can do your open house. And if you are a guest to us today, I hope you come back and celebrate. Usually about 50 exhibitors, researchers from all over the place that put out their best stuff to show and tell. And so it's a really great day to celebrate science that happens here locally. So just putting those on your radar. Other event that I just wanted to remind us of is that we do these seminars every single Thursday in this room at 3:30. So next week's seminar is February 27th, when Zachariah Muha, who's a postdoctorate research associate with the College of Earth, Ocean, and Atmospheric Science here at Oregon State University, is going to be asking the question, is it a regime shift or is it a resilient strategy for our rocky shores? So that one is going to be an interesting talk as well. So I hope you join us for that. But I want to get us quickly on to today's talk, which is going to be some work that is done locally, and we've been hearing about it, so we're excited. But let me introduce to you Margaret Conley, who is a 6-year PhD student with SEOS, working with Jim Lerzak and Rob Hetland, thank you very much. Jim is with OSU and Rod is with PNNL. And so she's been working here locally. She is interested in estuarine physical dynamics, in particular the dynamics and drivers of water temperature, as well as current and salinity, and how these physical dynamics affect estuarine ecology, such as the growth and survival of oysters. So her research includes observational and modeling work, which I think she's going to tell us a little bit more about today. So I'm going to quickly hand it off to Margaret. All right, take it away.
Does that sound good?
Can you all hear? A little louder? Okay. You are not giving me feedback, everybody. Okay, try again.
All right, I'll keep just started and we can adjust it later. So I'm going to talk about measuring and modeling water temperature in Yaquina Bay now and in the future. And this work is part of my PhD thesis with my advisor, Jim Lerzak, also with George Waldwesser and Melanie Fewings at OSU, and then with Rob Hetland at PNNL. So temperature dynamics in estuaries haven't been very extensively studied, and that's despite them temperature being kind of a basic physical variable that's really important for ecology and biogeochemistry. Just a few examples would be that temperature affects dissolved oxygen, it affects growth rates, and I have firsthand experience with that. This is what one of our sensors in the estuary looks like after 2 weeks in the summer. Happens really fast. In the winter, not so fast when the water is a little colder. And temperature is important for determining whether habitat is suitable for things like oysters, eelgrass, and salmon. With climate change, we expect to see warming water temperatures in general, and that can cause issues. You've probably read about changes in the occurrence of harmful algal blooms, disease transmission, and species ranges. And this is through the direct influence of climate change. So if the air is warmer, that can transfer heat to the water. But there's also a lot of indirect impacts, like changes in sea level, different precipitation patterns or flow of the river, and changes in cloudiness. And this is adding onto an already really dynamic environment, estuaries. So it's important to try to figure out how the temperature might change. The water temperature in an estuary is mainly determined by two processes. So if we think about like a cross section of an estuary, it's kind of like a trough, and we're pouring in river water at one end and ocean water at the other end. And those two things will mix together and produce some kind of intermediate temperature. So that's conservative mixing. But then we can also have heat exchange across the surface of the estuary. And this atmosphere estuary heat flux will depend on things like how windy it is, the strength of solar radiation, and also cloudiness. Temperature changes in an estuary occur on a wide range of timescales, so minutes to decades. In this talk, I'm just going to focus on two timescales. So we're going to look at some slower changes or low frequency changes. And we're going to, within that category, we'll look at cycles that have a period or a cycle length of months. So kind of the seasonal yearly cycle. And then we'll also look at some subseasonal variability, which is what we're calling changes on timescales of weeks to months. Things like the spring neap cycle and tidal amplitude. We'll also look at, so we don't have a long enough time series to look at like decadal trends or interannual changes, but that's where we're going to try to use a model to make some future projections with that. We're also going to look at some faster temperature variability, so things with higher frequencies or short periods, and this will be things on the timescale of days, which includes the daily solar heating cycle and the twice daily and daily parts of the tides. And those are particularly interesting because the solar cycle is exactly 1 day long, but the tides are a little bit longer than that. So the relative timing of like when it's noon and then when high tide is changes throughout the year, and that makes some interesting patterns. Both of these categories of temperature variability will change in time, and that's because we have seasonal changes in things like surface heat flux, the temperature of the river and the ocean, the flow of the river, and the tidal amplitude. And then we also see variability in space within the estuary. So if we think of an overhead view of the estuary, where we have the river on one end and the ocean on the other end, that sets up kind of a gradient in temperature along the estuary, where you have the two different temperatures and then a kind of a range between them. And so if you're located up here at the river end of the estuary, you might be more influenced by whatever the river is doing, whereas if you're located right by the mouth of the estuary. Also, because we have exchange across the surface of the water, you could see differences between locations that are right on the main channel of the estuary versus places that are in side channels or mudflats. Because if you have kind of a big shallow area with a small amount of water, that's going to heat up or cool off a lot more efficiently than the deeper main channel would. And then finally, another thing to think about with regards to temperature is that residence time is really important. So how long does water stick around in a particular location? And if you have water that's kind of sitting in one place for a long time, it could be acted upon by surface heat flux a lot more than water that's moving through the estuary really quickly. So the setting for our study is Yaquina Bay, which is a small drowned river valley in the Pacific Northwest. It's right outside the door here. Here we are at Hatfield. But if there's people who aren't in Oregon, you can see where we are in the state in the map in the corner there. And Yaquina Bay is actually a really interesting place to look at water temperature. So one reason is that we have pretty big tides here. The mean range is about 2 meters. So we can see a lot of influence from the tides and then also the difference between neap tides and spring tides. We also have a lot of really interesting sloughs and mudflats. So for example, there's this really big mudflat at Sally's Bend, right outside here, Idaho Flats. And then we've got these two big sloughs. So there's King Slough, which is pretty close. And this one is really wide and shallow with a lot of mudflats. And then farther upriver, there's Pool Slough, which is very different. It has kind of a small narrow channel with marsh on either side. And so those are two interesting locations that we looked at in our study. Yaquina Bay also has a pretty big seasonal contrast, which is a great way to look at differences in temperature between winter and summer. So for river flow, since we get like atmospheric rivers in the winter, we see big rain events where there's a lot of river water coming into the estuary. And it's really different from the summer when the river flow goes all down to almost zero. And it's a totally different river condition. We also have a pretty big cycle in the coastal ocean because we have upwelling in the summer. So we'll see really cold water coming in from the ocean side of the estuary. And that's contrast to the winter when there's more downwelling. And finally, we have a pretty big contrast in the surface heat flux between the summer and winter because of seasons. So we collected just over 2 years of measurements throughout Yaquina Bay at 9 different sites. This schematic map is showing all the different location measurements. The different symbols are showing different combinations of sensors, but at most sites we had surface temperature, and a few places we also had surface and bottom temperature, so we could look at the changes in depth. The farthest downriver site we had was right here at Hatfield on the pump station dock, and then on the upriver end, we went up to Cannon Quarry, which is a county park. We did some CTDs at Elk City. That's where the Yaquina River and Elk Creek come together, and that's the main freshwater input to the estuary. We didn't have a time series there, though. And we collected data from 2020 through spring of 2023. To supplement that, we also used some publicly available data. So we used, there's a river discharge gauge a little bit farther upriver at Chitwood, and we use that to estimate how much fresh water comes into the estuary. We also used data from the tide gauge here on the NOAA dock. And then from the Ocean Observatories Initiative, they have a inshore surface mooring that we use to figure out what kind of temperature and salinity water that comes into the estuary. Related to that, to do our analysis, we need to know what the temperature is of the river water and the ocean water that are coming in. So for the ocean, we used that OI data, and then we estimated the river temperature using our farthest upriver site at Cannon Quarry. And then the last thing we needed to know was how much heat is being exchanged across the surface of the estuary with the atmosphere. To do that, there's not enough measurements on the ground to calculate all those things, so we used weather model data from a weather model of the Pacific Northwest. So this is an example of data from just one of our measurement sites, and we see a lot of temperature variability on a bunch of different timescales, kind of all combined. So this is showing, this figure has 3 different locations on it. The blue line is data from Oregon Oyster Farm. You can see on the little map up here, it's kind of in the middle geographically of the estuary. And so that's the blue line on the top 2 figures, on the top 2 panels. And then in those, we also have the gray line, which is showing the ocean temperature, and then the black line, which is showing data for the river. And so in the top panel, we're looking at surface water temperature at each of those places. And then in the middle panel, we have surface salinity at all of those locations. So that's kind of telling us what kind of mix of river and ocean water we're seeing, because the river water is always fresh. And then in the bottom panel, we're looking at a couple factors that influence the temperature dynamics. So we've got the discharge from Yaquina River, that's the black line on the right-hand axis. And then we have in the blue line, the light blue line is the net surface heat flux, kind of an hourly basis. And then the dark blue line is a low pass version. So looking at kind of the longer variability in that. So there's a lot going on here, but I'd like to point out how you can see some of the influences on the water temperature just by looking at the time series. So first of all, if we look at in the summer, if we look at the ocean temperature, you could see that there's these big oscillations in ocean temperature that are associated with upwelling events. So when it's upwelling, the ocean temperature is really cold, and then if we get a wind relaxation, it gets kind of warm. So that's what this peak is, and then it gets cold again and warm again. And those signals and variability kind of work their way into the estuary, and we'll see that showing up in our estuary sites. So you can see the blue line during this really strong upwelling. We have really cold temperatures at high tide in the estuary. It's the ocean water making its way in. And then when the upwelling relaxes, then the high tide temperatures aren't as cold. We also see the influence of rain events on the temperature. So this is an example in 2020. We had these two really big storms about a month apart. And then during those events, we see that the temperature throughout the estuary kind of all goes to the same value. It's like this huge amount of water just comes in, and whatever temperature the river is everywhere in the estuary becomes that temperature. So you can see all three lines kind of going to the same value there. And that happened throughout the time series every time there was a big rainstorm. The last thing we can see is some of the influence of the surface heat flux. So that's this time series here. And you can see from the darker line that it tends to be positive in the summer. So usually it's a warming influence. And then in the winter, it's closer to 0 and sometimes slightly negative, so more of a cooling influence. And we see that when the surface heat flux starts to be positive around March, we start to see estuary temperatures that are actually warmer than both the river and the ocean. So the warm water has to come from somewhere. It didn't come from either end, so we think that's from surface heating of the estuary. And that was especially strong in this year. Although we can't really look at long-term trends over time, we can compare the 2 years in our study because they had some pretty distinct conditions. So in 2021, there was much stronger upwelling than in 2022. And we did see overall cooler ocean temperatures, and there was a more pronounced difference when we had wind relaxations during that summer. We also had a really interesting year in 2022 where the spring was really much later than usual. So in a more typical year, I think like 2021, you see that we had some rain in February, and then it kind of petered off, and then we have basically no discharge starting in June, even a little bit earlier. In 2022, it kept raining. It was raining in March and April and May. And so it finally stopped raining in June. And then that's when it kind of went to more of a summer condition. But the river temperature was a lot colder that year, probably related to that weather pattern. Finally, we also happened to record data during the heat dome in 2021, which was a kind of a notable heat wave, especially for the coast, I think. And so we did see some influence from that. You could see there's kind of relatively high heat flux during that time period. There was a local maximum in the river temperature. And I actually noticed that we recorded the highest observed surface water temperature that we recorded was during that event, which was at Paddle Park, which is this site a little bit higher up the estuary, which was 28 degrees, which is pretty warm. But it wasn't actually that noticeable at other sites in the estuary. And I think that's partly because during that period of time, the low tide was in the morning, so it didn't happen like right in the afternoon, and it was really hot, and that might have reduced the impact of that event compared to some other places in the Northwest. Okay, so it's interesting to look at the time series, but when we look at it, like in the top panel of this view, it's all the timescales of variability are kind of mixed together, and it makes it really hard to understand what's causing the temperature to vary at these different scales. So what we did is we separated out into components. So we take out 2 different low frequency components. So seasonal cycle, which is everything that has a period between greater than 3 months. So that includes like the annual cycle and then things in that range. And then we also pulled out what we're calling subseasonal variability, and that's everything with a period between 36 hours and 3 months. So kind of the scale of like weather events going through or spring neap variations in tidal amplitude. Finally, we pulled out the high frequency variability. So here I'm showing you kind of everything that's left, everything less than 36 hours. And then later we're going to actually split that up into the daily and the twice daily cycle to see if there's any differences between those. And this makes it easier to see how kind of the patterns in each part of the temperature variability are caused by different things like changes in the river and ocean temperature or spring neap cycles. And so this brings me to my research questions. So we're trying to understand how temperature varies in Yaquina Bay now, and then also what will it be like in the future. And so to do that, I'm going to show you some examples of how temperature varies at low frequency in the subseasonal and seasonal timescales. And we'll look at how that variability changes over the course of the year, and also how it's different between different locations in the estuary. Then we'll do the same thing for some of the high frequency changes, the diurnal and semi-diurnal cycles. How is it different, in summer and winter, and how is it different when you look in different places? And then I'm going to introduce a model that we've been working on of Yaquina Bay, which is really still a work in progress, but we're going to use it to make some projections of future temperature. So first we'll look at some of the low frequency temperature variability. So looking at the seasonal cycle, we found that temperature has a fairly large seasonal cycle, and it's also pretty different in between years. So the seasonal cycle is generally the biggest part of the temperature variability, and you can see that in the upper panel here, we're looking at just the seasonal part of the temperature variability at 6 different locations in the estuary plus the river and the ocean. And so that's the top panel, is the surface water temperature seasonal cycle. I'm also showing you the seasonal cycle and the net surface heat flux at the same locations. So this seasonal cycle can be up to about like 15 degrees in the summer. You can see, especially at the upriver locations, we have a pretty big swing in temperature between summer and winter. One interesting component of it is that we get, so in the summer, we have this pattern along the estuary where the ocean is coldest, and then moving up the estuary, the sites are kind of neatly lined up where it's coldest at this end, and then it gets warmer and warmer and warmer, and then the river is the warmest. But there's an interesting deviation from that. So the 2 dashed lines on here are, the orange one is King Slough and the green one is Pool Slough. So those are locations that aren't on the main channel. They're kind of off on these side channels. And if you just line these sites up in their order of where they would be on the main channel, like if where King Slough opens out onto the main channel, you might expect it to be a little bit colder than Sawyer's Landing because it's closer to the ocean, but it's actually warmer. And the same thing goes for these other sloughs. So they seem to be relatively warmer than you would expect in the summer, given their position. Then in the winter, we actually have the opposite pattern in space, where the ocean is usually the warmest, and then it's colder going up towards the river. So we have an interesting kind of a long channel temperature gradient. In the summer, there's a really big gradient, and it's warmer at the river. And then we go to fall, and then like in November each year, kind of everything is the same temperature, and then it flips upside down. And in the winter, it's just a little bit warmer in the ocean, or sometimes there's not much of a gradient at all if we're having like an atmospheric river. We also have some interesting contrast between the 2 years, like we were seeing in the previous figure. So you could see in 2021, these ocean temperatures are a little bit colder, associated with a stronger upwelling. And then in 2022, the river is a little bit colder than it was in 2021. We had really rain really late into the year. And that seems to have produced a much longer time period when all of the estuary sites are warmer than both the river and the ocean. It lasted more like 3 months, whereas in this year, it was only about a month. So some of these patterns in surface temperature seem to be clearly related to patterns in like the temperature of the river and the ocean water that are coming in, but there also seems to be an influence from surface heat flux. And so we can look at this graph, this part of the graph, and see that there's a kind of a similar shape cycle, but there's an important difference, which is that the surface heat flux is actually largest at the coldest sites, which is kind of counterintuitive. So like the value of the surface heat flux in the summer is actually larger at Hatfield than it is at like Paddle Park farther upriver. The reason that we see this is because since the water at Hatfield is colder, it's going to receive, there's going to be more heat transfer from the air to the water because it's cold, so there's a bigger contrast. And it's also losing less heat to the air. But it doesn't heat up like you would expect it to, since we've got all this heat going into it, because the water at Hatfield just keeps getting washed down into the ocean by the tides. And the same goes for the ocean itself, right? If you calculate how much heat is going into the ocean in the summer, there's a lot going in because the water is really cold, but upwelling just keeps delivering a bunch of cold water to the coast. And so we have all this cold water in the ocean, it comes into the estuary, and it keeps it from warming up at those downriver sites. At the upriver sites, we do see a lot of warming, partly because the river is warm, but there's not actually a lot of river water coming in the summer because the flow is so low. So partly it's also from it being heated up by the sun. the timing of positive surface heat flux in the spring also lines up with when the estuary starts to warm up. So you can see in March, both years actually, the surface heat flux starts to be positive, and then we see the estuary warming up. But interestingly, the estuary actually starts to cool off while there's still positive surface heat flux. So this is suggesting that we've got kind of a balance where at some point, the cold ocean water coming in kind of takes over and things start to cool off, even though there's still heat coming in from the atmosphere. Okay, so now I'd like to look at some of the subseasonal variations. So we see this big seasonal cycle. We can see how it's related to the river and the ocean temperature and the surface heat flux. Now we want to understand why we see temperature variations of, plus or minus a few degrees that are happening on this kind of weekly to monthly time scale. And this is the same figure as before, but I've also added a black line for the river and a gray line for the ocean. So if you just look at this wiggly line, you could see like some of the wiggles line up and some of them don't. It's pretty complicated, but some of the variability in the river and the ocean at this weekly timescale could be causing some of the variability in the estuary. Another thing that's on this figure is gray shading in the background. And those gray bars are showing when it's a spring tide, and then in between them is a neap tide. And so that's another factor that we're going to look at, whether the spring and the neap cycle is related to some of these changes in the temperature. And so to figure out if those things are related to each other, we did a correlation analysis. And here I'm showing in this figure with the squares is the R² value for correlation between, in the upper two rows, we've got 6 different sites in the estuary. So the subseasonal time series at each of those sites. And then we looked to see if it was correlated with the subseasonal ocean temperature and river temperature. And we did see some relationships. So you can see, first I want to focus on the first 2 rows. So there's a pattern in the strength of the correlation where the darker colors are a stronger correlation. So if you're closer to the ocean, like at Hatfield, there's a pretty strong correlation with the ocean temperature. And then as we move up the estuary, the correlation gets weaker and weaker. And then when we're at Paddle Park, there's really not much correlation with the ocean at all. And then we see the opposite pattern for the river, where the river subseasonal variations are really strongly matched with Paddle Park. But then as you go farther from the river, closer to the ocean, it gets weaker. There's an interesting difference between the sloughs and then the same location at the main channel. So if we look at Sawyer's Landing and King Slough is here, Sawyer's Landing is here. So they're kind of at a similar distance from the ocean, but King Slough has a weaker ocean correlation and a stronger river correlation. So even though it's kind of in the same place in the estuary, it behaves more like the river temperature. And we think that's partly because in the winter, those sloughs do have their own like little freshwater creek inputs, which is probably a similar temperature to the main river input. And then also because they might be a little bit more isolated from the ocean. Similarly, if we look at Oyster Farm and Pool Slough, which are this pair of sites, Pool Slough, which is off on the side, has a little bit stronger river correlation and a weaker ocean correlation than Oyster Farm, which is on the main channel. So we can also see how these signals from the ocean travel up the estuary. And this is by looking at the lag between the time series when we do the correlation. So the temperature at Hatfield is about 1 day behind the temperature in the ocean. So like if we have a wind relaxation in the ocean, about a day later, we'll see that happen at Hatfield. And then as you go up the estuary, you can see the signal kind of traveling. So after about 4 days, it finally makes it to Paddle Park, and it's also a lot weaker at that point. So we definitely see that when the ocean temperature changes, that makes its way into the estuary. And when the river temperature changes, that also affects the estuary. This correlation analysis also shows us that longer residence times tend to promote surface heating. We can see this through the 3rd and 4th rows of the table. So the 3rd row of the table is showing the correlation between the temperature at each site, and then what I'm calling surface heat flux here is an integrated version of the local surface heating at each site. So it's kind of like adding up the heat input or output from the atmosphere at each site over time and seeing if we have a warm week, do we then see a corresponding signal in the temperature at that site? And you can see that that correlation is really weak at the ocean end of the estuary, and then it's getting stronger as you go upriver. And that matches up with the pattern in residence time in the estuary, especially in the summer. If you're closer to the mouth of the estuary, the residence time is pretty short, so that water is getting exchanged a lot with the ocean. But if you're up in the upriver part of the estuary, like up here, the residence time tends to be a lot longer, where the water is just kind of hanging around up there. And so it makes sense that if that water is kind of sitting there, especially in the summer, if we have warm and cold weeks, that pattern is then going to show up in the water temperature upriver, but it might not show up here at Hatfield, where the water just keeps getting exchanged with the ocean. In the last row of the table, I'm showing the correlation between tidal amplitude and the temperature at each site. And it kind of looks just blank. There's a really small negative correlation, but it's really small. So we were kind of intrigued why there would be a negative correlation there. And so what we did is, instead of looking at the correlation over the entire time series, so like the all 2.5 years at once, we split up the time series into little 3-month pieces. And we're like, is there a correlation during these 3 months? Is there a correlation like during the next 3 months? And so we can make kind of a time series of the correlation. And that showed us that this is an example for oyster farm. So if we look at 3 months of temperature and 3 months of tidal amplitude together, sometimes they're really strongly anti-correlated, which is why we're getting a small negative signal. So you can see these values are pretty strong negative correlation, but then sometimes it's not correlated at all. And so when you look at the whole thing at once, we get kind of a weak signal, but it turns out they are related, just not all the time. So what we see here is a pretty strong anti-correlation between tidal amplitude and the temperature at that oyster farm, but only in the spring and summer. So during neap tides, which are small tidal amplitude, we get warmer temperatures. And we think we see that mainly in the summer because in the winter, it's just raining a bunch. The water's just going right through the estuary. There's no signal. But in the summer, the water's kind of sitting around in the top part of the estuary. And it's during neap tides, when the tidal currents are smaller, there's less tidal mixing. The residence time is a little bit longer than it would be during a spring tide when the tide range is really big and everything gets mixed around. And so if it's warm out, it'll tend to warm up during the neap tide, and then the signal kind of goes away during the spring tide. Okay, so next we're going to look at some of the higher frequency changes in temperature. So we see at these longer time scales, it seems to be like during neap tides, when currents are small, we get warmer temperatures and more influence from surface heat flux, but it depends on the time of year. And then so we want to look at some of the daily and twice daily cycles in temperature and see what's causing differences in those over time. So we found that the high frequency temperature changes also change seasonally, and they're also related to spring neap cycles. And we can see some of that right away when we just look at the high frequency part of the temperature variability. So that's the bottom part of the graph here. And there's two things you might notice. One is that the size of there's like a blob here, right, and here, that's during the summer. So there's much bigger temperature swings on the daily time scale in the summer than there are in the winter. And then another thing we can see is that the biggest temperature swings line up with the shading. So they happen during spring tides. And then there's smaller temperature swings during neap tides. So those are two interesting patterns. But to kind of understand those better, and also to be able to look separately at the daily cycles and the twice daily cycles, because both of them can be caused by tides, but then the sun cycle is only going to produce a diurnal temperature change. So if we want to kind of untangle those and figure out like how much temperature change is caused by the tides and how much is caused by the sun, we used something called a wavelet analysis, which is a frequency analysis that tells us how much the temperature is varying at a bunch of different frequencies, and then also as a function of time. And then when we use that analysis, we can pull out a time series of the temperature variance, or like the amount of temperature change as a function of time in different frequency ranges. So that lets us say, okay, how much is the temperature varying on the twice daily cycle as a function of time, and then how much is it varying on the daily cycle? And so that makes a figure like this. This is the temperature variance for semi-diurnal periods, so cycles that last 8 to 16 hours. So that would be the twice daily part of the tides. And then in the bottom panel is the diurnal temperature variance, so 16 to 32 hours, which could include both the daily part of the tides and the heating by the sun. And you can see that the semi-diurnal and the diurnal variants share some characteristics, but they're also different in some really interesting ways. So well, some of the shared patterns is that the variance is a lot bigger in summer. So you can see these values are bigger and then really small in the winter and then bigger in summer. And so if you think back to when we looked at the comparison between the river and the ocean temperature in the summer, we had like that 15-degree difference. And so when we have tides, that gradient kind of moves back and forth along the estuary. And in the summer, since it's a big gradient, you'll see a big swing in the temperature. In the winter, everything's kind of the same temperature anyway, so like you can move it back and forth, but it doesn't matter. So that kind of explains why we see these big temperature swings in the summer. We also see that these peaks in the semi-diurnal variants line up, especially in summer, pretty neatly with the shading. So they're happening during spring tides. And that makes sense for the same reason, right? So a spring tide is just a bigger tide. So if we have bigger currents, then we'll get a bigger temperature swing than if we have a neap tide when it's just a smaller temperature swing. However, the two graphs are different in some ways. And the most important way is that there's actually some peaks during neap tides in the diurnal variants. They seem to only happen kind of in the spring. You can see some of them here. So it's peaking in between the shaded areas. So there's bigger daily temperature swings that are happening during neap tides. So if that was just because of the tidal movement, that wouldn't make sense. This was a smaller tide, so we wouldn't expect to see a bigger daily swing in temperature from that. So we think those peaks are coming from during neap tides, surface heating is more effective in warming up the estuary and making like a daily swing in temperature that's because of the sun. Again, because the currents are smaller during a neap tide, and so there's less tidal mixing, and that signal comes out better. During the spring tide, it could be heating up, but the water just gets mixed out and we don't see it as much. So we think this is similar, kind of a similar process to what we saw at the subseasonal timescale, in that the neap tides are allowing surface heating to have a stronger influence, but now it's happening kind of more on a daily timescale. We also see some interesting differences between locations in the same variance of the temperature. So this is the same figure, except now we're looking at two different sites. So we have, we're back down at the mouth of the estuary at King Slough, off in the side channel, and then Sawyer's Landing, which is a similar distance to the ocean. So Sawyer's Landing looks a lot like Oyster Farm did on the previous slide. It's got these big semi-diurnal temperature swings in the summer. They're lined up with spring tides. Similar diurnal variants with some of the neap tide peaks in the spring. But then King Slough is just like totally different. It's kind of similar semi-diurnal variants, so it's not as strong in the summer. But what really stands out is this just like ginormous diurnal temperature variance between March and June. We don't see this anywhere else. It's like totally weird and unique to this site. So for some reason, the diurnal variance is really large at this location. And we think it's because King Slough is really muddy and shallow. And so in the spring and summer, when it's hot and sunny, we just think the water's getting really hot on a daily basis on the mudflat. And then we're getting these really big diurnal swings in temperature associated with surface heating. But if we look upriver at the other slough, so at Pool Slough, is totally different. So this, I switched to now showing Pool Slough and Oyster Farm together. And so the green line is Pool Slough and the blue line is Oyster Farm. You can see they're pretty similar. There's not a big difference between them. So even though Pool Slough is off on the side channel, it looks a lot just like the main channel. And Pool Slough doesn't have a lot of mudflats. It's got kind of more of a deep, narrow channel with marsh on either side. So it just doesn't seem to have as much surface heating as King Slough does, where it's all kind of bare mud and there could be a lot of surface heating going on. We have another piece of evidence for surface heating being really important in King Slough, which is measured surface and bottom temperature there. And in the summer, we see like 10-degree warmer water on the surface than on the bottom, right as the mudflats are draining off from the high tide in the morning. So we think that's another piece of evidence that there's just a lot of surface heating there related to kind of the shape of the slough and then also the timing of the tides. Okay, so we see that there's a lot of interesting temperature variations in Yaquina Bay now, but we also want to understand how water temperature might change under a future climate. And so to do that, we've been working on a model of Yaquina Bay using the finite volume community ocean model, or FVCOM. So this graph shows the model domain is the little purple box here. That's the location of the OOI offshore mooring, which we use to help characterize the ocean for the model. And then we can zoom in and see this is the offshore part of the model domain. And the reason we have such a big chunk of ocean in there is because we don't want the edge of the model to affect what's happening in the estuary. We're not really interested in the ocean. We just want to know what's going on in the estuary. And so that's kind of a low resolution part of the ocean. And then the stars in that part of the figure are showing the other OI moorings that we used to put data into the model. And then finally, we can zoom in and see the estuary. And so here the colors are showing bathymetry. So that's the depth below mean sea level. So you can see the main channel of the estuary is about 10 meters deep, and then gets shallower up here. And so if you notice the little grids, grid pieces of the model are triangles. So this is an unstructured grid, which is helpful for kind of doing a good job capturing the really irregular coastline in the model. It's a 3D model using primitive equations, and it has wetting and drying, which means it can take into account that you have like mudflats that are wet during high tide, and then they're exposed at low tide, and it can handle that. The resolution we used is about 10 meters within the estuary, and we did that so that we could try to resolve the channels. Like in King Slough, you can see these little darker areas. So those are the mudflat channels in King Slough and in Sally's Bend, and the channel in Pool Slough, because we really wanted to try to capture how those areas affect the dynamics of the overall estuary. And to control the model, we put in temperature and salinity for the ocean. We use the OI data for that. Then you kind of you add tides at the ocean boundary. And to do that, we used a tide model that we added subtidal variations from the NOAA gauge so that we could represent like sea levels higher in the winter because of downwelling. And then on the river end of things, we used data from our observations to make a time series of the river temperature, and then we have the flow from the river gauge. And we only have the one river in the model from like the Elk City area, because we don't have any way, I mean, there is fresh water coming in other places, but we don't have any data about it. So the model does a pretty good job. I have a little video here. It's still a work in progress, but it does a pretty good job representing the estuary temperature and salinity. So we're modeling summer and winter from 2021, so we can look at the different seasons. And here I'm showing the surface temperature and salinity oyster farm. And then if I add the model on top of that, see it's a pretty good match. We're still working on adjusting some of the parameters in the model. So the goal is to get the model to match our observations as good as we can in the present day. And then we can use the model to kind of do tests to figure out what happens in the future or in a different condition, which we can't do in the real world. And so one way that we've been able to use the model to understand kind of the relative importance of the ocean and river temperature and the surface heat flux is that in the model, we can just turn surface heat flux off. You can't do that in the real world, but so that's actually really interesting because like, okay, like there's no heat exchange. Like how wrong is the model when we just mix together the river and the ocean temperature? And so we did that. So this is showing the observed temperature, and this is the model temperature when you don't have any surface heat flux in the model. Then we've got the river and the ocean for context. So you can see that the model is too cold in the summer. So even though the estuary doesn't get really hot in the summer, that heat flux is key in getting it to the temperature it does get to. We're about 10 degrees too cold without any surface heat flux. So in the model, when you don't have heat flux, it's just kind of a mix of river and ocean water, and then there's just like a tiny amount of river water coming in, so the ocean kind of takes over and it gets really cold, colder than it should be at like an Oregon oyster farm, for example. We can see that if we want to understand like how much heat is coming into the estuary from surface heat flux, we kind of add that up over the course of the summer. We see it's consistently positive, so it makes sense that the model is not warm enough when it's missing this heat flux coming in. But also at the end of the summer, even though there's still heat coming in from the heat flux, the estuary doesn't keep warming up. So there reaches, there's kind of a balance equilibrium between surface warming and ocean cooling in the summer. The situation is really different in the winter. So this is running the model in the winter with no surface heat flux. And it's actually not that bad, even if you have no heat flux in the model. There's some small errors. This is on the same range as the previous figure, just to show the different size of the error. So, it looks pretty good at this time. So we can zoom in, and there are some errors, obviously. But this is telling us that in the winter, the most important thing is whatever mix of river and ocean water we're getting, and that's kind of setting the temperature, which is very different from the summer when the surface heat flux is more important. I mean, if we also kind of estimate how much heat is happening from surface heat flux, it's mostly a slight cooling effect. So if there was only surface heat flux, we'd expect the estuary to cool off more, but in the winter, we have pretty low residence time. The water is going through pretty fast. And so we end up with this kind of intermediate temperature. And that cooling is balanced by river water coming in. So in conclusion, we see that there's a lot of different timescales of variability. And when you add them all together, we get really interesting but complicated patterns of water temperature in the bay. And it seems like residence time is a really important thing that determines when you get what this importance of surface heat flux is at different times of the year. So we see kind of a neap tide heating effect, but only in the spring, especially in the spring and summer, when there is, especially in the summer when there's low residence time, so that the heating you can see the effect of it because the water is just sitting around in the upper part of the estuary. Whereas in the winter, even if there was a lot of heat flux, we wouldn't be able to tell because the water is going through the estuary so quickly. We also found that there's differences in residence time between winter and summer that are important, also between different locations, upriver versus downriver. And then we saw the really interesting big diurnal cycles in temperature in King Slough, which we think also has something to do not only with the fact that like maybe during a neap tide there's less mixing and so there's more surface heating, but also that there seems to be a lot of heating going on in spring and summer. And there's also, so another factor that could be at play here is that we have an annual cycle and when the lower low tide happens. So I'm going to get mixed up, but I wrote it down so I wouldn't get it mixed up. So lower low tide happens in the afternoon in the winter, and then it shifts to the morning. And so then as that's happening kind of in the spring and summer, we can think about those low water levels mostly happening during the daytime when surface heating is happening. And that could help heat things up. Whereas during the winter, when that's happening at night, it could also cool things off, but we have less of the heat fluxes tend to be smaller in the winter. So that relative timing pattern is kind of a yearly cycle that could also be affecting what we see. But the dependence of surface heating on like neap or spring tides is actually really interesting because, if we have a heat wave during a spring tide, we might not notice the effects as much as we might if we had a heat wave during a neap tide. So that could affect, how much different weather patterns actually affect the estuary. To understand the future water temperature in the estuary, we plan to use our model to make some future projections. And what we can do is, since it's a model, we can change like the air temperature in the atmosphere. We can change the temperature of the ocean, the temperature of the river, and we can also adjust the sea level. And so we're going to do what's called a pseudo global warming experiment, where you change the boundary conditions of the model. And then we can see like if we have the sea level that we're going to have in 2100, how is the temperature different? And how could those changes affect things like temperature thresholds for oysters for their preferred growth range, or for other species that live in the estuary. Okay, so thank you very much for listening. I just want to acknowledge some of the funding sources that supported this research, and also thank the generous people who let us use their docs to collect data, which was really awesome, and then all the people who helped with fieldwork. And I'm excited to hear your questions, and you're also welcome to email me.
Wonderful. Thank you so much for getting through all that great data for us. We're going to switch to question and answer, and we'll start with folks online. Roseanne, any questions online? Okay, for folks online, if you have a questions, go ahead and put it in the chat. How about questions in the room? All right, make me run for it. I'm coming. Slowly but surely.
Yeah, it's an awesome talk, awesome data set. And the frequency analysis is super interesting. And can you explain again why the semi-diurnal tidal signal kind of disappears in the winter?
Yeah, that's great. So in the winter, the temperature doesn't really vary that much along the estuary. It's either sometimes it's a little bit warmer at the ocean, or sometimes it's actually kind of the same temperature everywhere, especially like during a big rainstorm. And so even though the tides are moving the water back and forth, if it's all the same temperature, we don't get a big signal. There's not a lot of variance in the temperature on the tidal timescale versus in the summer when the temperature is really different as you move along the estuary. And then when the tides move that, we see a big change.
Other questions in the room? I'll ask a question. I'll get you in a second. So a lot for the observed data, once you spend a little bit of time with it, some of this is expected. So what was the most unexpected part of this from the observed data? What took you by surprise?
That's an interesting question. I don't think, I guess the kind of the complicated patterns in the, especially in the variability, like at the weeks to months time scale, I don't think I was expecting to see so many things going on kind of from week to week. And there's really common, like, so I showed the variation in time and how the tidal amplitude affects the temperature and how it's like strong in the spring and the summer and not at other times of year. There's also some interesting patterns in like how much the surface heat flux affects the temperature if you look at those as a function of time, which I didn't show. But I think it's really interesting how different it is like in spring versus in fall. Like I kind of expected like, okay, so during the neap tides in the spring, when the surface heat flux is positive, we see that it gets warm. Maybe in the fall, like when the surface heat flux is negative, we should see it getting cold, but it doesn't. So there's kind of like inconsistent things like that, where there seems to be, I think maybe from the timing of when low tides are or something like that, that favors certain seasons. But
nice talk. I enjoyed it. Yeah, I was wondering if your substrate type might be also variable to your model. You've referred to these as mudflats. With the mudflats, there are some covered with eelgrass or alder or some vegetation type that might also affect the temperature.
yeah, definitely. Were you asking if there's if you put
where were your stations? Were they all in mud, or were some in eelgrass? And
yeah, so in King Slough, we didn't see eelgrass. I don't think any eelgrass except like as big clumps that floated by and got stuck on our sensors. So that was, I think King Slough is mostly bare mud. We had a site at Sally's Bend, which would intermittently have like a ton of eelgrass, but like deep, not growing there, like washed up there. So that was also bare most of the year, except when there was things washing up on it. And then in Pool Slough, a lot of our sites were like attached to floating docks mostly. So like in Pool Slough, the banks are steeper and there's marsh grass on the high like on the banks. And then our sensor was actually like on a dock that, so it would always be at the surface of the water. If that answers your question, kind of.
Describes your situation, but I was, well, in King Slough, you also had oyster plots there.
Yeah.
So that would be, that's a different substrate type than mud.
Yeah.
Okay.
Sorry, I'm not, like, is there,
well, you're basing, I didn't want there to be, did you purposefully choose to measure temperature on mud substrate as opposed to other substrates in the bay?
No, we didn't do that on purpose. And like the temperature sensor is not, we didn't measure like the mud temperature.
No.
Just the water temperature in the nearby, I guess.
But they may be different substrate might be radiating different heat levels of heat.
Yeah, I suppose, like a oyster shells could reflect
Right.
more sun than like bare mud would for sure.
And another minor question, I guess, is there's been a lot of research done in Yaquina Bay. Practically all the studies that I'm aware of in Yaquina Bay, they also measured temperature. So there must be a lot of data in the historical data that might be used to test your model further. I don't know.
I don't know of a ton of historical time series of temperature. George Waldbusser had some studies going for a few years before where they have a couple sites. And I know there's a EPA work where they did a model of future water temperature using kind of a more simplified model that's not 3D. And they had a couple time series, but they weren't multiple year time series as far as I could tell. So I bet there is some data. The trick is like having more than one location, and then like, when there's a bunch of holes in it, it can be hard to figure out what's going on, but good thing to look for.
I'm sure EPA here has a lot more historical data on water temperature.
Mhm.
Yeah, I'm going to take the mic over to our EPA representative, but we have a question online. So go ahead, Roseanne.
Have you or are you planning to model how major large-scale events in the ocean, like major marine heat wave or El Nino event that impacts the coastal ocean, would affect temperatures in various locations in Yaquina Bay?
Okay, yeah, that's an interesting question. So you certainly could do that with our model. I have to finish my PhD kind of soon, so I'm not sure I'm going to do that. But you can change what temperature the ocean is, so you could simulate a heat wave. The way we're doing it is just kind of taking so right now I'm modeling the year where we took data so I can compare it to the observations. And then we're going to add like an offset to that and say, okay, so now we have a future ocean. What does Yaquina Bay look like? But you could also do something where you added like a heat wave event and then see what happens in the estuary. And I would certainly guess, like if I was to hypothesize about that if the ocean was really warm or like we didn't have as much upwelling as usual, it would make at least this end of the estuary warmer than it would otherwise be.
Hi, Jim Caldy here with EPA. And just to address Steve's question, we have a number of data sets, both historical, and there's actually one that's currently in progress where we're measuring temperatures on the mudflat, both
cool.
water column and sediment temperatures in the lower estuary in a number of different habitats, including eelgrass, bare sediment, and that. And what we've been really interested in is sort of the disconnect between where we measure temperature, like in the channels, versus the temperatures that the biological communities intertidal communities that we're interested in, and what they're actually experiencing. So I would really love to talk with you more about how we might be able to collaborate with some of that stuff.
Yeah, it's really interesting on the mudflat. We would see in particular in King Slough. So our sensor was kind of in one of the small channels, and in the summer we saw there was time periods when the surface was like 10 degrees warmer than our bottom measurement, and we think it's like there was a high tide, and then that all the water on the flat draining into the channel, and there'd be this periodic periods where it was just really hot right at the surface.
Yeah, we've seen temperatures up to about 30 degrees C on the mudflat.
Really hot.
Yeah, really interesting. Thank you.
All right, I think we're at time, but it sounds like some collaboration is in your future, perhaps, even though you're going to try to get out of here and graduate. We'll make it more complicated for you. But I just want to say thank you so much for sharing with us and being a part of this. I appreciate it very much. For folks in the room, again, thanks for being here. If you didn't sign in to the little sign-in sheet when you came in, please do so. That helps Margaret keep track of how many people were in the room and gives her credit for giving this talk today. So please sign in. For everybody, again, thank you for being here. I hope to see you next week and possibly at the Science on Tap event on Tuesday. Thanks, everyone. Thank you, Mark. I'll take care of it. So you all can.